All right. Hello, everyone. This is a video to replace the class on on Thursday morning. Yeah. This is the continuation from the previous class on Laplace transform. Yeah, in this video, I think I will explain a little bit further about the Laplace transform and maybe some application regarding the systems, yeah, the LTI systems, control systems in general. So I think the general um, direction is we go towards studying control systems, and this would be the material that uh, would be considered from or for the midterm exam. So the topic or the material is up to this this material, this video. So make sure that you understand what's going on. So okay, so previously we have I think, okay, let me turn off the video. Okay, so previously we have the uh, you know definition of a Laplace transform, which is basically the extension of the Fourier transform, right? As we knew already, so some signals, unfortunately, they do not have a Fourier transform, and that's why they are, not convergent, right? So they cannot have a Fourier transform, and they have to be analyzed with a Laplace transform, which is able to do that because of the concept of the region of convergence, the ROC. So this is the region of convergence of the equation here, right? Of the transfer function of the um, xs here. So if we have this function or the signal xt is minus e to the power of minus at times u to the minus t. So this is clearly the unit step, but it's uh, inverted, or it's the value is 1 if the time is negative, but the value is 0 on the case in the case when the time is positive. So in this case, we have this kind of region of convergence, whereas in the first half here, on the first example, we have this region of convergence. So this is called unilateral Laplace transform, whereas this is so this is the causal, this is the anti-causal. So this is considered the unilateral Laplace transform when it starts from time zero, which means this unit step. But this is not the unilateral Laplace transform. It actually stops at time zero. So the region of convergence here is the one here, with the this area here, and this area here is uh, the complement of the area we have in the left figure. So in one, for the same Laplace function for the same xs, we have different ROC. So it is possible that a Laplace transform, it has different characteristics, or it has different stability property depending on the region of convergence. All right, so yeah, those are some examples. So yeah, this one I think we have also discussed last week about the region of convergence. If xt is the right-sided, which is the first example we had, the line here will be the border of the area, the convergence area and the non-convergence area. And if it's the left-sided, the line here is also a border, but what we consider is what's less than sigma, which is the real value of the frequency. So again, we are talking about the complex frequency here, the S, right? In the Fourier transform, we talk about the imaginary one, but here we talk about the complex, which means the real one plus the imaginary one also. So this is the Laplace transform table. I think I tried to show you yesterday or in the previous meeting, but I haven't put this into the slide. Now I did put this into the slide. So these are some commonly used functions such that the unit impulse signal, the Laplace transform is 1, and this is the region of convergence. So if we have a unit step, the Laplace transform is 1 over s. We have the minus yeah, u to the minus t, so it has the same Laplace transform, but it has a different ROC and so on. So yeah, there are some interesting feature that we have to pay attention to, such as the ROC, the transform, and the transform could be the same for the different signal, but they have different region of convergence. Okay, right. So yeah, so let's continue by discussing the properties of the unilateral Laplace transform. Again, unilateral Laplace transform, it starts from time 0. So okay, let me try to, okay, I think it's okay using this. Yeah, so usually we add ut or we multiply the functions by ut. So if you have like a e to the minus at, it's multiplied by ut. So this is called the unilateral Laplace transform because it has the term ut here, which implies that it starts at time 0. So the common properties. So yeah, previously we have studied this for Fourier transform, right? So that should not be too much difference. That shouldn't be, that different from the Fourier transform. It's similar. Uh, in some cases, we just replace the j omega. We just replace the j omega into s, right? So for the function x1 t here, the Laplace is x1s. If we have Fourier transform, we define this x1 j omega. For example, if we have Laplace transform, we just replace this by s. So this linearity property, I think, is the same with the Fourier transform. So you have 10 ut, and you have 5 times e to the power of minus 2t ut. So this is the Laplace transform. So basically, we can, we can perform the Laplace transform in each term here if they are added or this is an addition. If this is a multiplication, of course, we cannot, right? We will see later. But for addition, I think this is convenient because if you have like two different terms, you just perform a Laplace transform in each term, and the result is just the summation of this, right? So here there are two poles, or the one that makes this 0, makes the denominator 0, which is minus 2 and 0. So the region of convergence here is the one that's most positive, which is 0, based on the one that's most positive. So ROC is the real value of S more than 0. Okay, so the next property is the time shifting. This is also similar to the Fourier transform. So if we have the function xt, we take a Laplace transform, it becomes xs. Then the Laplace transform of this xt times ut to the minus t0. Of course, t is also delayed by t0 or shifted by t0. Here the time shifting characteristic, it makes the function not not that much different from xs. We just add this e to the minus t0s, so t0 is this one. It's called the delay. right? So it's delayed by t0. So here we don't need to change, you know, that much, but we just need to multiply this by minus t0. T to the power of minus t0 s. So a simple example here is the Laplace transform of a rectangular signal, which could be represented by the difference of step signals. Right? So if you have step signals, let's say here, 0, right? So this is ut. If you have ut minus 10, which means that it has the value beginning from 10, right? So this is 10. So the difference of the signals is this, basically. So this could be represented by this Laplace transform in the complex frequency signal. So 1 over s is from ut, u to the t minus 10 is from e to the minus 10s over s, which is this, right? So 10 is the delay, and now we obtain 1 minus e to the minus 10s over s, and the ROC here is the same as ROC of xt, which is the real value is positive, right? So this is the one we have for unit step signals rather. Okay. Um, okay. So we change this. All right. So for S shifting, so this is another way to represent the delay, but now the delay is in the frequency domain. So if we have this xt, then the Laplace of the e to the power of s0t is xs minus s0. So for example, if I want to find the e to the minus 2t, so this is delayed in the frequency domain, right? So now we replace the s here. S is replaced into s minus minus 2. So this is plus, this is minus, right? So s0 here is minus 2. So xs minus s0, which means that xs plus 2, right? So now we replace s to s plus 2, and we replace s to s plus 2, and it becomes this fraction. So yeah, the region of convergence here is that the real value of s has to be larger than minus 2, because this is the considered the pole minus 2, right? Yeah, so this form of cos, let's say cos xt or cos at times ut is present in the table as well. So if we take a quick look at the table, so it's here, right? So here, if it's multiplied by e to the minus something, e to the minus a, so we replace s to s plus a, for example, right? Okay, so I think this one is not used that often for the context of this course, but I think it's just nice to know. So the next property is the time scaling. So the time scaling different from the time shifting. If time shifting, it's t minus a. Time scaling is let's say t over a or ta, right? So if the Laplace transform of xt is xs, so this is the region of convergence, then now we have this Laplace transform of x of the alpha t or at, here we used alpha. So it's 1 over alpha times x of the s over alpha. The region of convergence is real value of s is more than alpha sigma 1. So if the original uh, region of convergence is more than sigma 1. Here the region of convergence of this function is more than alpha times sigma 1. An example is if we have a unit step of the 5t, right? So if it's ut, then the Laplace is 1 over s. If it's u 5t, the Laplace is, we follow this. So it's 1 over 5 because alpha here is 5, right? And then multiplied by 1 over s over 5. So s over 5 is from s over alpha 5, right? So we just replace s to s over 5. And then it just, it happens to be the same here. So s over 5, it would be 5 over s, right? So it would be like 1 over s. So that's the Laplace transform of u of the 5t. But it's not always the same, right? So if you have like, for example, e, to the minus 2t, for example, you have the value here. But if you kind of multiply this by 5, it'd be like 5 times 2t. It would be uh, yeah, we just use this, but of course it's different, right? Because this is e to the minus 10t, would be like a 1 for um, s, s plus 2 here would be like 1 over s plus 10, or if it's multiplied by this u 10t, of course it would be also different. So yeah, those are some properties as shifting and time scaling of the Laplace transform. All right. I think the next property is important for the context of this course. So we have the differentiation in time domain, and later we also have integration in time domain. So this basically converts the differential equation into just an algebraic equation, right? So if we follow the first, or we follow the topic of solving differential equation, in the beginning of this course, maybe a few weeks ago, we know that it's difficult to solve a differential equation. We have to find the homogeneous solution first, and then we have to find the particular solution later, and so on. So for this, uh, or by this Laplace transform, it's actually relatively easy for us to solve the differential equation. So if the Laplace transform of xt is xs, then the Laplace transform of a differential equation, or the first derivative of xt, um, is sxs minus the initial value of xt. In this case, it's x0. And the Laplace transform of the nth derivative of xt is basically s to the power of n xs. The rest of this is the initial value of xt, which should be available. Um, but in some cases, or in control systems in general, it's often assumed that this is 0. So it's just s to the power of nxs. So this is based on the initial value. An example is the solution of the differential equation. Of course, we try to find the solution of this. It's hard if we try uh, to use like finding the homogeneous solution first. There are some structure that we have to obey. There are some formats where the solution is in that format only. For example, it's the e to the minus something t if you have the first order and second order. We have some different structure and so on. So we'll try to solve this, using Laplace transform, which it is easier, right? And we don't have to memorize like the forms of the solution in the differential equation. So at least in differential equation, especially for constant coefficient, it's yeah, relatively easy to solve. So for example, here we have y dot dot. Y dot dot is the second derivative of y. So it's basically says this, right? And then plus 5y dot plus 5y is 0, and we have the initial value or the initial condition is that y0 is 5 and y dot 0 is 1. So the procedure, of course, here we have actually done this with Fourier transform, right? We do the same here. And I think it's a little bit easier because we replace the j omega with s. So in terms of solving the at least in terms of notation, it's simpler, right? So we just use s here instead of j omega, and also it's easier to do the inverse, which means we just look at the table and we could obtain like the time domain of the function given the complex frequency function that we have. So we perform a Laplace transform. Y dot dot plus 5y dot plus 5, 4y is a Laplace transform of 0, which is just 0. So again, y dot dot becomes s square ys minus sy0 minus this is the xn minus 1. So n here is this should be x to the n minus, no, not the power, but this is the derivative, right? So I will try to clarify later. So s times y0, and then this the last one we don't use s, so this would be s to the power of 0 actually, but yeah, it's equal to 1. Y dot 0, and here it's 5 sys minus y0, and then the next term here is just 4ys. So we just plug in this value, right? We just plug in this value of y0, which is 5, also y dot 0, which is 1. So s square plus 5s, this is 4, because there is also um, yeah, 4. So I'm looking at this 4, so this is 4, and also this is uh, 5, right? So now we have, yeah, so this is s square ys, this is s square, and we have plus 5s is we have a 5s here, so we have plus 5s. It ends up being plus 5s, and then we have 4, we have minus 5s, and we have 6, which is equal to 0. Okay, so now we have s square plus 5s plus 4, and we have 5s plus 6. We just move it to the right hand side, and we obtain a ys is a 5s plus 6 over s square plus 5s plus 4. Now, by using the table, or first by performing the decomposition of the partial fraction here, fraction s square plus 5s plus 4, we arrive and we get yt equals yeah, 1/3 over e to the minus t plus 14 over 3 to the times e to the minus 4, right? So then we obtain the the signal yt from this differential equation. I think it's relatively easier compared to using only the time domain differential equation solution that we discussed previously. Okay. Yeah, another example here is we obtain the Laplace transform of t to the power of 3 ut. Another approach or one approach that we could use is we consider xt as t to the power of 3, which means that we know that x0 here is 0, so we can obtain the initial value from the function's value itself. And x dot t here is 3 uh, t square, which is the derivative, and x dot 0 is 0, and x double dot 60, or x double dot t is 60, and x double dot of 0 is 0, and x triple dot of t is 6. So yeah, we can now um, put this together. So s to the power of 3 xs minus s square times x0 minus s x dot 0 minus x dot 0 is 6 over s. So this is, from the fact that we use the derivatives. Now, if we want to find this Laplace of x dot dot dot, of course, it's s to the power of 3xs, and this is minus s square x0, and then it's a minus s x dot 0. And these values we have obtained previously. So x0 here we obtain from this, which is 0, x dot 0 is also 0, and also x dot dot 0 is also 0. So we get rid of all of this, and Laplace transform of 6 ut is 6 over s, and then we obtain that s to the power of 3 times xs is 6 over s, and xs is 6 over s to the power of 4. Okay. Okay, let's pause a little bit. All right, so we continue here by the integration in time domain and also differentiation in the S domain. So integration in time domain is, the complement, or, the jewel of the differentiation in time domain, where in the differentiation we put S, we multiply the Laplace function by S, um, and the integration in the integration in time domain, um, we have the um, Laplace transform of xt is xs, and if yt is the integral of x tau d tau from 0 to t, then Laplace transform of ys is 1 over s xs. So we basically just divide this by s, or just multiply this by 1 over s. This will be used very often in the context of systems where we will see later what's called like integrator. So integrator is basically we multiply this function by 1 over s. So this is called the integrator. And for S domain here, in the S domain, if we differentiate xs, so xs here is this integral. So if xs is the integral of xt e to the minus st dt, then the derivative of xs is minus t xt e to the power of minus st dt. And therefore, we can get the differentiation of S domain here is equivalent to Laplace transform of the time domain, the xt times minus t, and so on, right? If we have d xs derivative, the nth derivative of xs, now the Laplace of the inverse Laplace, let's say, of this is the minus t to the power of n times xt, right? So now, if in the differentiation in time domain, we have s times xs. Now we have minus t to the power of n for the nth derivative times xt. Well, one example here, we could obtain the Laplace transform of the fundamental function L, sorry, R. So we perform the Laplace transform of R, which is t times ut, where we can see here Rs is minus d over ds Laplace transform of ut, which is minus d over ds 1 over s, which is 1 over s squared, right? So this follows from this. So if we have uh, t times ut, so we put the negative here in the right hand side. So we get 1 over s is the Laplace of ut, and we differentiate 1 over s, it becomes 1 over s squared. So in general, t to the power of n ut is, the Laplace transform is n factorial over s to the power of n plus 1. All right, so the next here is modulation, but this is not used very often for systems in general. So we'll just go this briefly, go into this briefly. So if we have a Laplace transform of xt, which is xs, then we have a Laplace transform of xt times cos omega 0 t, and Laplace transform of xt sine omega 0 t is this. So we add or we subtract by j omega or minus j omega, so half of this, and also for sine is 1 over 2j times the difference between x of s j omega 0 and s minus j omega 0. And yeah, one example here is we could obtain this, e to the minus at cos omega t. So we have this. It's actually, the same as here we can use other method, which is the time delay, the one that we discussed in the previous slide. And also another way is we could use the modulation property to obtain the Laplace transform of this function e to the minus alpha t times cos omega 0 t times ut. All right, so the next property that is very important is the convolution. So we will use this very, very often for this course for the systems. And basically, yeah, it's the same as the Fourier transform, where we have a convolution of two signals in the frequency domain. If we have the convolution in the time domain, the frequency domain, the equivalent here is we just have a multiplication. So if we have xt star ht, the convolution of this, right? So this is actually the Laplace transform of this is the multiplication of x and h. So one example is we obtain the unit step response of the system with impulse response ht. Again, ht is the impulse. response, and xt here is the input, right? So for unit step, it means that the xt here is ut, which means the Laplace transform is 1 over s, right? And ys here is hs times xs, because it should be yt is ht star xt. Here we have 1 over s plus 5, which is the Laplace transform of this, 1 over s plus 5. Um, yeah, sorry, I think yeah, this should be negative. Let me change this a little bit. Yeah, okay. All right, so now we have yeah, hs times xs. So hs is the Laplace transform of this, which is 1 over s plus 5. And xs is the unit step function. Xt is ut. Xs is the Laplace transform of ut, which is 1 over s. So we have 1 over s times 1 over s plus 5. And yeah, we have 1/5 here, 1 over 5 times the difference of this. So this is the way we perform what's called the partial fraction, which is yeah, which is discussed after this. So we have to obtain this, terms, right? So we cannot work with this multiplication in the denominator, but we have to work with an addition or subtraction, because that way we could use the yeah, the table, the Laplace transform table. So by the linearity properties, if we have this, again, we could have like this. We could solve this one by one, term by term. So 1 over s is 1, 1 over s plus 5 is e to the minus 5t. Okay, so now we obtain yt as 1/5 times 1 minus e to the minus 5t u. Okay, so the next property is the initial value and the final value theorem. So initial value, if xt is the differentiable around t equals 0, then we know, or we can obtain the initial value of xt, which is the limit s approaching infinity of sxs. So if we have such signal, xs is 10 over s multiplied by s plus 5. We could, approach this s with the infinite value. So times s, right? So this would be s times xs. So we could, get rid of this, and we could plug in the infinite value here, so it becomes 0. And the accompanying theorem here is the final value. I think this is important because we can know the steady state response, or how the system, how the signal ends, or is it ending at time, or is it ending at the value, let's say like 0 or infinity, or let's say some constant such as 5. So we could know that by this final value theorem. We don't need to know the xt, right? But we could know, yeah, we could obtain this by looking at the Laplace transform xs times s. So the steady state response here, we obtain the steady state response of a system with the impulse response and input, respectively. This is the h and this is the x. Okay, so let me change this one more. All right, so we have now, ys is hs times xs. So HS here is the um, 1 over s plus 5, and yeah, from e to the minus 5t, and xs is 1 over s. Now we can know the limit of yt, t approaching infinity, which is the limit of s, s multiplied by 1 over s multiplied by s plus 5. So we basically get rid of this, and we plug in the value 0 here, so it becomes 1 over 5. So we know that if we have the system, the final value of that system, or the final value of yt, is actually 1/5. We don't even need to to know what yt is, right? So yt is unknown, or we don't solve yt here, but we know that the limit yt t approaching infinity is 1/5. Okay. It is similar. The difference between these two theorems is that for this t is approaching 0 initial value. Here is t approaching infinity, the final value. But we use the opposite for the frequency domain, s approaching infinity, and here s is approaching 0. Okay. All right, so the next step here is to discuss a little bit about the inverse Laplace transform. So, so far, actually, we have done that by looking at the table, right? So if we have the function xt, the Laplace transform of xt is xs, and if we perform the inverse Laplace transform, yeah, it becomes xt again. So, um, yeah, from this to this, we could, do the integral. We could use like, the integral of xt e to the minus st dt. But what should we do if we want to do the opposite from xs to xt? Well, turns out that there are several approaches. So the first is the contour integral. So for the contour integral from s equals sigma plus j omega, we could obtain the formula of the inverse Laplace transform. So we could obtain this back, xs times e to the st ds, integrated over s, the frequency, and it's integrated from sigma minus j omega to sigma plus j omega over 2 pi. But it requires us to know this one, right? So this is different from integration over time, where time is always real, right? There is no imaginary value of time. But for frequency, complex frequency, there is imaginary value j omega. So it's actually difficult to solve this with the contour integral. So instead, we will focus on the other method here that considers fractions and polynomial, so that we can again consult the table to form like, or to find the matching function of the value, or the function xs, right? So again, yeah, we focus on this fraction and polynomial, and what we try to do is we look at the table. Okay. Okay, so this is the partial fraction method. So this is one way to obtain the function, time domain function given the frequency domain function xs, or ys or hs. So uh, usually we will have this ratio or this fraction ns over ds. which is could be written as this term T1, T2 until Tk. T1 is it's either of this form, T2 is also either of this form, and so on. Where here we rely on the fact that the polynomial s plus p, the denominator, here and also s square plus as plus b here is irreducible, or it cannot be factored further. So there are three cases. So case one here is we do not have repeated first order factors. Case two here we have first order factors, but it's repeated. And case three here we have second order factors. So now we have the unique or non-repeated first order factors. We have xs. Here is ns over ds. Of course, n is the numerator and the ds is the denominator. And we try to, you know, we try to solve ds, or we try to factorize ds into several polynomials here, s plus p1, s plus p2, and so on. That's if we have one or the first order factor, which means we have s plus something, we could form this fraction ns is now a1 over s plus p1 plus a2 over s plus p2, and so on. And we could actually find the an here through this, so we basically plug in our value of s plus pn. Suppose that this is s plus p1, so this would be s plus p1. And we multiply this with n over d, so which is the entire fraction, but we plug in the value of s equals to the minus pn. And now we obtain an, right? So with the same method, we obtain, a2, a3, and so on. And time domain function xt here is the Laplace transform, the inverse Laplace transform of xs of this. And if we obtain this way, if we obtain this fraction, we can look at the table basically, or I think we can also memorize that. So a1 here is the coefficient here, it becomes the coefficient here times e to the minus p1 p, and so on. Right, so we obtain xt is basically a summation of an exponential function. All right, so this is some examples of the one with the first order factor. So first example here is the inverse Laplace of xs s plus 1 over s square plus 8s plus 15. So the answer here, of course, we could factorize this s square plus 8s plus 15 into s plus 3 times s plus 5. So a1 over s plus 3 plus a2 over s plus 5. A1 here s plus 3, s plus 3, this would be s equals minus 3. So as per previous slide here, we have s equals minus pn. And we basically cancel this term, right? So we have now s equals minus 3. This would be a minus 3 plus 1, minus 2 over 2. So this is minus 1. Can do the same with a2. Actually, it's, we can do this by doing this, for example, s plus 3, s plus 5. This would be s plus 5 plus, a1, a2, s plus 3. right? So we could do this, and we can find the value of a1 and a2. So this would be similar to s plus 1, you know. So what is the value of s? So the coefficient of s is clearly 1 here. So a1s, for example, plus a2s is 1, and so on. We could find the coefficient by solving the linear equation. Uh, but this is like a, you know, some a faster way to to obtain a A1 and A2. Uh, well, of course, you can do both. If you could memorize this, it's good. But if you cannot, then we can always use this old conventional way to find the coefficient by solving the linear equation. So now we arrive at the xs here is equal to minus 1 over s plus 3 plus 2 over s plus 5. Then xt is the inverse Laplace of xs, which is minus e to the minus 3t plus 2 times e to the minus 5t ut. So from this, we can obtain xt from this fraction, which happens to be exponential function. The same method could be used for example 2. Now example 2, the key here is we need to factorize this, right? So it's s plus 1, s plus 4, which is equal to s to the power of 3 plus 5s square plus 4s. So xs here is s minus 2 over all of this, and we could factorize this into a1 over s plus a2 over s plus 1 plus a3 over s plus 4. So by doing this, of course, to find a1, we set s to be 0, right? So s, like s, s minus 2, s power of 3 plus 5s squared plus 4s, s is 0. Or actually we should factorize this as s plus 1, s plus 4, right? So if we plug in 0 here, would be minus 2 over minus 2 over 1 times 4. So would be minus half, right? So the same could be done with A2 and A3, and we obtain a XS, which is, if we have minus half here, if we have just S, so just minus half, and 1 and minus half, and this is basically UT, right? So it's a minus half times UT, plus e to the power of minus t, UT, minus half e to the power of minus t UT. All right, so the next is the repeated first order factor and also the second order. Uh, so for the first order factor, if it's repeated, we have to consider an and ak. So we cannot just write this one time. We have to write this n times. If there is like a s plus 1 square, so we have to consider s plus 1 and also s plus 1 square, not only s plus 1. So now we have an s plus p to the power of n times n over t, um, where s is minus p. So the one that makes this 0 similar to before. But for ak here, we have to consider 1 over n minus k factorial s plus p to the power of n. So the difference is we have this, and we have to differentiate this. So it's a little bit more complicated, but let's see how we could solve this. Now for the second order, we have to make sure that we cannot factorize this further. So for example, s squared plus s plus 1, we cannot have like an imaginary value, right? We cannot have like a complex value in this polynomial because we cannot have the Laplace transform otherwise, right? So that would be s squared plus p1s plus q1. So the numerator now becomes a1s plus b1 and so on. Like, so this is the first order numerator for the second order denominator and so on. So it's actually a little bit tricky to find this, and it's also limited to only like the first order and the second order. Otherwise, it's beyond this method. All right, so these are some examples of the repeated first order. Okay, let me pause a little bit. Okay, so for the repeated first order, we have two examples here. So for the first example, we try to break down the denominator of this s square plus 2s plus 1, which is s plus 1 square. So of course, we have to consider both s plus 1 and s plus 1 square in the equation. So a1 here is the one with s plus 1, but a2 is the one with s plus 1 square. We solve the a2 a2 first. So yeah, we take the value of s equals minus 1. So here we have s plus 1 square. We just cancel this with s plus 1 square. So s is minus 1. So this would be minus 1 plus 2 equals to 1. And a1 here is this 1 over 1 factorial. We have to uh, differentiate this s plus 1 square. So of course, what we do is we try to cancel this, and then s plus 2, we differentiate this, and then we plug in this number. So it's just happen to be 1. So it's 1 over s plus 1 plus 1 over s plus 1 square. Right, so we have Laplace, inverse Laplace of this. So this is exponential one, and this is the exponential also with time, polynomial. So e to the minus t plus t times e to the minus t ut. Now for the example 4, we want to find the inverse Laplace of xs, which is 8s minus 4 over s to the power of 3 minus 3s square minus 9s minus 5. So xs here, of course, we break this down, the denominator into s minus 5, s plus 1, and s plus 1 square. So here B, this one is the one without the power of, the advanced power. So it's just S minus 5 times what we have here, 8S minus 4 over S minus 5 plus S plus 1 square. So here S is 5, and we cancel this. We plug in this value, it would be 1, right? 4 over um, oh, sorry, not 4. Here it's s is 5, so this is 6. This is 30 36. Yeah, this is 6 square, so this is 1. Okay, and for A2, it is the same as the A2 here. We have S plus 1 square. We cancel this. Now we have 8S minus 4 over S minus 5. And now we have this A2 equals to 2. And A1 here, we have to be careful. Here we have this cancellation, of course, and we have to derive this, right? So deriving this is difficult. Well, it's a little bit more complex, you know. So U or U over V, if you try to differentiate this, it would be like u, or if you try to differentiate it with respect to time, for example, this is u, uh, u dash v minus v dash u over yeah, v square, if I remember correctly. Yeah, please check. Yeah, so this is u, the whole term here, and this whole polynomial here is p. So yeah, we have to differentiate here with respect to s, of course, and then we differentiate, and then we substitute the value -1, and we arrive to the value -1. So xs here is this 1 over s minus 5 minus 1 -1 over s plus 1 plus 2 over s plus 1 squared. So we obtain xt here is e to the minus or e to the 5t minus e to the minus t plus 2t e to the minus t ut. All right, so the next example here is concerning the second order system. So suppose we have this um, fraction s plus 6 over s to the power of 3 plus s square plus 4s plus 4. Now the xs here it's broke down into s plus 1 times s square plus 4, which is for s squared plus 4, we have to obtain this a and b into this form, as plus b, whereas for s plus 1, we obtain this c uh, as usual. Right, so c is the easier one, so we just cancel this and we plug in the value of -1. So that would be like 3. This is 3. This is sorry, 3. Yeah, -1. Uh, right. Yeah. Okay. So yeah, where were we? So yeah, this is -1 square plus 4. Yeah, this is 5. So this is 5. So this would be 1. And xs here, we have to solve this, by doing this conventionally, or we have to, solve for a and b by linear equation, right? So we have this s square plus 4 plus 1 over s plus 1. This is s squared plus 4. This is as plus b times s plus 1. So yeah, now we get as square plus a plus b s plus b. Uh, we increase or we add this by s plus s square plus 4. So this would be a plus 1 and a plus b and b plus 4. So all of this should equal s plus 6, right? So by solving the linear equation, we have a is -1, b is 2. So this is a little bit longer. And now we have xs minus s. So this is s square plus 4, which is 2 square, s square plus 2 square, minus s plus 2 over s square plus 2 square. So um, why are we differentiating, or why are we, um, separating this? Is that we are going to look at this function of cos and sine. So if it's a cos, we have s over s square plus the frequency omega 0 square. And if it's a sine, then we look at the frequency omega 0 plus or over s square plus omega 0 square. So in this case, it's sine 2t. This is a cos 2t. This is plus e to the minus t. Then course, all of them should be multiplied by ut. Right. So yeah, that's for the second order system. This is another example. Um, so of course we do the same here. So we first solve the easier one with s here. So s equals 0. We cancel this. Um, we cancel this, right? And then we plug in the value of 0, which is 5 over 5, which is 1. So we have c equals to 1. And then xs is a plus 1s squared plus b minus 4s plus 5. Yeah, so all of this should equals this, right? And we find a is the 1, b is 10, and s plus 10. Here we separate this into s minus 2 and 12 to obtain the term e to the power of 2t plus 12e to the power of 2t, yeah, cos t and sin t respectively, plus 1 multiplied by ut. So yeah, the tricky part here is we have to be we have to be familiar with this kind of form, right? At the beginning, in the beginning, it may be a little bit overwhelming, but yeah, with some exercise, I think we could solve this. We could, we know like quickly, oh, I have this kind of fraction. So in frequency domain, I have this fraction. In the time domain, it's equivalent to this fraction, and so on. Not this fraction, sorry, this signal, and so on. Okay, so that's for the second order system. First order system, non-repeated. Also, first order system repeated. We have at least obtained some insight on how we uh, find the inverse Laplace transform by looking at the fractions. Okay, so let's pause a little bit. Okay, so the next topic here is the system stability and in the S domain. So as we know, stability is an important issue in system design, and BIBO stability or bounded input bounded output stability could be analyzed in S domain through transfer function, and the transfer function of LTI system is represented by the ratio of polynomials in S domain. So you have HS, which is the ratio of the numerator n and the denominator d. So if this is written in the form of partial fraction, we have Hs is A1 over S plus P1 plus A2 over S plus P2 and so on. And the impulse response of the system here is obtained by taking the inverse Laplace transform of Hs. So Hs here is called the transfer function. Which we will go into later. Now, there are what's called poles and zeros. So pole here is the one that makes the denominator 0. So if you have like a s over s plus 2, well, here pole is 2, right? Sorry, minus 2. Yeah, if you have a, let's say s plus 1 over s square plus maybe 4s plus 5, or maybe 6s plus 5, poles are minus 1 and minus 5, right? And for this, the impulse response system, HT is e to the minus sigma t for the simple poles in the left half plane of S domain. So if you are talking about stability, I think what we are talking about is the location of the poles. So if the pole is in the left half plane, then the impulse response is like the one, this one, right? But if the poles are on the imaginary axis, meaning here, here the impulse response is a sinusoidal. Um, Whereas if the poles are in the right half plane, the impulse response or the poles are located here, the impulse response is e to the sigma t, which is positive sigma. So here it has negative sigma, it has a zero sigma, and here it has positive sigma, and it affects the stability property of the system, where if the poles are in the left half plane, the impulse response becomes like that, and it becomes stable, Bible stable. But if the poles are on the imaginary axis, here the impulse response becomes like this, and the poles or the stability of the system, they are marginally stable. And if the poles are in the right half plane, the impulse response becomes like this, and the system is Bibo unstable. The response here becomes unbounded, as you can see from this equation. So this one is, significant in determining how the system behaves. It would be like this. Here it would be like this. Here it would be like this. Okay. Now, those are for simple pole, which means the pole, there is only like one value in that pole. So what if there are several values or multiple values of the poles? We call this a multiple order poles. And multiple order poles here in the left half plane is minus sigma plus minus j omega. So what matters here is this, this minus sigma, and this is bistable since the decaying of the exponential component is faster. Uh, Also for the right half plane is the same. It's in the previous slide. So here the impulse response is like this. Ht is t to the power of m, e to the power of sigma t times a cos omega t, and b sine omega t. And the system is Bibo unstable since the response increases for increasing time t, right? Also, actually, for the poles on imaginary axis, S equals j omega to the power of m. Here, the system is Bibo unstable since the system increases for increasing value of t. So there is some differences. So there is some difference here. If the previous slide here, in this slide, if the pole is simple, it is marginally stable for the case where the pole in the or on the imaginary axis. But here, if there are multiple poles on the imaginary axis, the system becomes Bibo unstable since the system or the impulse response increases for increasing value of t. All right, so these are some examples. Um, Example 7 here, we are asked to determine the system stability that is represented by the differential equation y triple dot plus 5 y double dot plus 5 y dot equals to minus 2x plus x dot. And this is could be, could be solved by obtaining the transfer function. So if we remember from the previous examples, if you have this, it would be s y to the power of 3 s, right, plus 5s square y s plus 5 s y s and so on. So if they don't say anything about the initial condition, just assume that it is zero. So we don't need to worry about that. So this would be minus 2x plus sx. Yeah, so this would be s minus 2 over s to the power of 3 plus 5s squared plus 4s. So hs here, this is ys over xs. So the poles here are located in this, and this, because the pole here is the right most pole, or the most positive pole here is at s equals 0. Here it's actually marginally stable, but we could consider this stable as well. So this should be marginally stable. Now, what if we have this? So we have s plus 2 over s squared plus 2s plus 1. Here the transfer function is, of course, we could factorize this into s plus 1 square, and we have multiple poles at s equals minus 1. And then the system here is stable because, yeah, the poles are negative. And um, if we try to transform this back, or perform an inverse Laplace transform with ht is e to the minus t plus e to the minus t ut, which means that the exponential component here, e to the minus t, it is more dominant than the linear or the polynomial one in t here. So if you have, for example, t very large, this one would be close to 0, and this one is also close to 0, so that T here is, like, it's not really effective, it's not really effective to change the value of HT. So the next example here is HS. The numerator is s squared plus 6s plus 5, and then the denominator is s times s squared minus 4s minus 5. So now we have the pole at s equals 0 and s equals 2 plus minus j. And then the system here, they are not stable because, well, you could factorize this, right? Using like a ABC formula, minus b, and then plus minus square root of b square minus 4ac over 2a, for example. And we obtain 2 plus minus j1. And since the real value here, the real parts of the complex pole is positive, then we know that the system is not stable. All right, so that's about the remaining of the Laplace transform. I think I still have some more slides. Let's continue a little bit. All right, so now we continue. Um, Yeah, this is just a short slide about the transfer function and the block diagram. So this one we have done this actually, right, in the previous slide. So I think the order is a little bit not very tidy, but yeah, let's see. So uh, transfer function here is basically HS, the ratio between the input and the output. So this HS here is the transfer function, and um, yeah, it connects the input to the output, right? So previously, the to obtain the output, we have to perform the convolution operation to get the output, to obtain the output from the input and from the impulse response, xt and the ht. And from this Laplace transform, using Laplace transform approach, we could obtain the HS, which is the ratio between ys and xs, which is also the Laplace transform of ht, small ht here. which is the impulse response, right? So this is called impulse response. This is impulse response. This is H is the transfer function, which is the Laplace transform of impulse response. Okay, so suppose that we have impulse response H, which is the summation between 5 e to the minus 2t plus 2 times e to the minus 10t. Here we get the transfer function. Hs is the Laplace transform of H. So again, from linearity, we get 5e to the minus 2t plus 2e to the minus 10t ut. So this would be 5 over s plus 2, and this would be 2 over s plus 10 from the table, or of course you could, do it by hand, and it will be, the result would be the same. So this from this, we can get this fraction 7s plus 54. So we get the poles, they are minus 2 and minus 10, and the 0, uh, yeah, they are minus 54 over 7. So we get the poles and we get the zeros of this. All right, so yeah, again, ball is one that makes the denominator 0, or the root of the denominator, whereas 0 is the root of numerator, or those that makes the numerator 0. Now, yeah, let's talk a little bit about the system properties and the ROC, the region of convergence and the stability. So for causal LTI system, HT uh, HT0 if the time is negative. Here there is this is considered or called the right-sided signals. For anti-causal, it's called the left-sided signals. Uh, Oh, sorry. So this should be t more than 0. Let me change this. Okay, so for stability, for a stable LTI system, the region of convergence has to include J omega axis, or this real value equals 0. And for a causal and a stable LTI system, the transfer function has to contain the poles in the left half plane of S domain. So here uh, the transfer function here, the poles, they have to be, all of them should be in the left half plane of S domain. Yeah, the one I think we have discussed this one in the previous slide. So an example here is suppose we have a system represented by the transfer function Hs S minus 2 over S plus 2 over S minus 4. So this one, if we don't know the causality of the system, we could arrive at three different ROC, right? So we know that there are two poles, and also there is 1, 0. So if the system here, if they are causal system, they will have the ROC here. Uh, yeah, the black part here. And if the system here is uh, not causal, so they will be here where they have their stability. And if the system they are also not causal, uh, they are unstable. If the ROC here they are unstable, right? So ROC here depends, of course, on the ut, whether this is multiplied by ut or multiplied by minus u minus t and so on. So this determine the causality. Usually we assume that the system is causal, which means that we don't need to worry about whether this is a causal system or non-causal system. With the unilateral Laplace transform, we imply that the system is indeed a causal system. So if we have this, unilateral Laplace transform, and we have the pole -2 and 4. Since this is not satisfied, there is one pole that is located in the right half plane of S domain, then we conclude that the system is not stable, and so on. All right, so the next part here is this is just again maybe a little bit you know repeating what we have done before. So to obtain the transfer function, we basically can perform the Laplace transform in each term of the differential equation. So if we have kth derivative, we have kth derivative here, we perform the Laplace transform in each of that. And the same with Fourier. Actually, with Fourier, we multiply them by j omega. With Laplace, we multiply them by s, and so on, right? By the linearity, we can get rid of the coefficient. And it's actually common to assume zero initial condition, so we don't need to worry too much about the initial conditions, such as let's say x 0 or x dot 0, or maybe x triple dot 0, and so on. We don't really assume that unless it's explicitly stated. So yeah, we can obtain the impulse response here is the inverse Laplace of Hs. Also, it's possible to analyze this S domain. I mean, in terms of how we eliminate and how we are able to model the, let's say, the electrical circuit or even the mechanical system and so on. We can do that in the S domain. So yeah, we could find the model and its constant coefficient dE by performing Laplace transform and perform the elimination in the S domain. So we are asked to obtain Hs and Ht for the system or the circuit below with EI as the input here, and the VRC, the voltage in the capacitor and resistor as the output, and zero initial condition with all of these resistance, inductance, and capacitance, they are all at 1. So EI here is LDI plus IR plus 1 over C integral I dt. So VRC, this is from Kirchhoff voltage law, right? So all of the voltage here has to be zero, the summation of all of this voltage. And the VRC here, this is the definition. VRC is I times R plus 1 over C integral IT dt. And if we perform the Laplace transform here, it would be EI equals to LS I plus IR plus I over SC. So VRC here is, yeah, we just basically change this small I into capital I, and we just change the integral into 1 over S, the same as the Fourier, right? So in Fourier, we change this into 1 over j omega. Now we change this into S. So yeah, at the end we arrive to this I equals SC over RCS plus 1 VRC. And of course, we could get rid of I. So by, um, substituting I here into this, right? Right. So yeah, this is EI. So we can get all of this, LS plus R plus 1 over SC. So yeah, now yeah, so we have this VRC, right? Which is I could be converted or could be yeah, change into VRC. So here we just do some substitution of I and the SC, so we arrive at this fraction, and HS here is the output over the input. This is the output is the VRC, and the input is EI. So yeah, that would be LCS plus 1 over S square LC plus SRC plus 1, which is S plus 1 uh, over S squared plus S plus 1 once we plug in all of the numbers. Actually, it's a maybe simpler if we just state the number here. L is 1, R is 1, C is 1, so that this would be is plus I over s, so that we can simplify the expression a little bit. So anyway, now we have hs is s plus 1 over s squared plus s plus 1. So this is not straightforward way to there is no straightforward way to find the inverse Laplace, and we have now s plus 0.5 over s plus 0.5 square plus 0.5 square root of 3 square. So why are we doing this? Because we are looking at this form of e to the minus 0.5t cosine uh, 0.5 square root of 3 times t, and so on. So yeah, that's ht here. From hs to ht, of course, we perform the Laplace inverse Laplace transform as we discussed before. All right, so the last topic here, this is the block diagram. So the block diagram here is a way to, to represent the system into some, let's say, some graphical representation. And it's used to describe the functional relation between components, and it's simplify the interconnection of the system. So this is, I don't know, this is in Indonesian, so um, you know, it illustrates how the input here affects the output. This is a DC motor, so you have the input in terms of voltage, right? And then you amplify the input, and then you have the load here, and then we have the velocity, or yeah, the rotation, in terms of yeah, velocity radian per second, for example, right? So yeah, basically this is like a simple block diagram of the DC motor, and for yeah, this is commonly used for systems, right? So the direction of this course is to analyze the system, and there are some fundamental elements. It says blocks here. It's commonly an S domain, and also this is a summing point. This is a take-off point, and this is the line with a row that determines the direction of the signals. So you have x here, you have y here, you have x plus minus y. Um, and then, yeah, we have the output z. Basically, we have the input x here. Yeah, this is just for the notation in this. We still denote the output as y, and so on, right? Okay, so these are some procedures to design a block diagram. I think some common fundamental operators are the constant gain K, and the integrator 1 over s. And some steps, they are to obtain first differential equation of the system, and then we obtain the Laplace transform of the differential equation, and then we design a block diagram from the obtained algebraic Laplace equation. And this is the same or similar to the simulation diagram. I think it's discussed maybe a few weeks ago in this course. So this is the summing point, and this is the takeoff point. Yeah, we can, add the RS with the CS, HS here, for example. So if there is a block here, it means that we just multiply this block with this. So if this is X, this is G, this is Y, it means that Y is G times X. But this is done only in frequency domain, right? If we have a system in time domain, we cannot do that. So that's why it's convenient to analyze the system in the frequency domain. This is a block diagram of the control systems or systems in general with the feedback. This is called a feedback when you have like the takeoff points here going back to the input, and yeah, with the addition and also with the multiplication and so on. Okay, so an example here, we are asked to show the block diagram of this RLC system as below. We consider zero initial condition. So this is the XT. XT is the input and YT is the output. So you have R, you have L here, and you have C, and you have the differential equation from the Kirchhoff voltage law. XT is IT times R plus L times di dt plus 1 over C integral of I dt. And using Laplace transform, XS here is just R times I. This is the same as the previous example, right? So LS times I, and you have 1 over C times 1 over S. And YS is I over SC, and so on. So we have obtained the yeah, this you know relationship between y and I other parameters. So we arrive uh, to this. Yeah. So this is we uh, change, or this is just y. So we can have like I minus ls over r. This is from the substitution of the first two equations here. So here we can actually draw some block diagram. So this is the first equation. You have xs. Um, oh, sorry, I think this is from this equation, xs, and you have a minus ys, and you have minus ls I, and it's multiplied by 1 over r. So this is 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 the output of this part of the block diagram, and also y is the multiplication between I times 1 over SC. So Y is, sorry, multiplication of this. So this is the block. So the one here, it has to be either a parameter, L, R, or C, or some integral or derivative operator. So you cannot put like IS here. IS is the one that changes over time, right? The variable, but here inside here, they are the parameter. So by combining these two, so we have a is here, and is here goes here again because it's the same. So this is just 1 over sc, right? So you have y here, and you have y here, right? So this is the same. as this one in the bottom. Okay. Um, yeah, so that's one example on how we can obtain a block diagram of a system here. You know, this is a system of electric circuit, the RLC circuit, and we can obtain the block diagram this way. All right, so there are several configurations of block diagrams. So this is similar to those of the the simulation diagram we discussed earlier in the last or in few weeks ago. So if we need to draw a block diagram for an LTI system represented by this, we could of course perform a Laplace transform, and we can do this. We obtain this equation s square times ys equals to s square times 2xs plus s multiplied by minus 3x minus 3y plus x minus 10y, and then yeah, this is type 1 solution. Type 2 solution, it should be maybe in hmm. Yeah, in a usual number, so Arabic number. So this type 2 solution, phi dot dot plus 3 phi dot plus 10 phi is x. So we kind of we kind of separate between x here and y. Here is this phi um, of this. So this is x, right? So we have x 2, 2x dot 2x dot dot minus 3 phi dot plus phi. So this is from this part. This is from this part. Sorry, this is from this part, the one in the left. So from this equation, we obtain the following equation from the Laplace, performing the Laplace transform s square Vs minus 3s Vs minus 10 Vs plus xs. And ys here is 2s square Vs. Of course, we perform the derivative or differential properties, and we get 2s square minus 3s plus v. Right, so that's a type 2 solution. It's represented in this figure. Type 1 is represented in this figure. Both are valid. Both are okay. You can do, whatever you want, as long as, the equation here is represented correctly. All right. So, okay, let me pause a little bit. Right now, yeah, we are going to briefly discuss about the algebraic operation of block diagram. So a system consists of several blocks or subsystems that are related in series, parallel, or feedback. In the S domain here, the transfer function that describes the subsystem relationships, it could be determined using algebraic operation. Again, so this is for series, this is for parallel, this is for feedback. If there are two blocks here that are connected to or connected in series, we can just multiply them. If they are connected in parallels, we just need to sum or add them together. If they are in feedback, so feedback here is a little bit unique. It's if this is called like a fit for part, and this is the feedback part. Fit for part offer one plus fit for times feedback. So this is the feedback part of this algebraic operation. So yeah, it's useful to obtain the response here. So this is commonly used in control system. we can try to obtain the transfer function of the system and the step response of this block diagram. So this is the feedback part, which means that we have to solve this, we have to solve this uh, according to the previous equation here, h1 over 1 plus h1 h2, and then the transfer function here is y over x equals to this part times this. So this is from the feedback part, the previous slide, 1 over s plus 2 plus 1 over 1 plus s here over s plus 2, or s times 1 over s plus 2, which means s becomes the numerator, and so on. Yeah, here we have this is done with like a usual usual algebraic equation. So algebraic operation. So we have 0.5 over s plus over s times s plus 1. So if we have the signal input xt equals to ut, then xs equals to 1 over s. The response here is ys is 0.5 over s over s plus 1 times 1 over s equals to 0.5 over s square times s plus 1. And we perform the partial fraction. Uh, yeah, and we obtain minus 0.5 over s plus 0.5 over s square plus 0.5 over s plus 1. Right, so you have a repeated factor here, s and s square, and you have s plus 1, which is the non-repeated factor. So now we can obtain the output from this block diagram. So if we previously try to show a system with a block diagram, now we do the opposite. We have the block diagram and we try to solve the system, or we try to analyze the dynamics of the system based on that block diagram. So yt here is minus 0.5 from this times ut, right? Plus 0.5t times ut plus 0.5 e to the minus t times ut. All right, so yeah, that's for this video. So of course, you will have a midterm exam on the October 31st. And yeah, we use the usual class, usual time, and material is until this class, the end of the Laplace transform. And you have a chance to bring your cheat sheet or bring your note, one A4 note, double sides. You can do this both sides. You can put whatever you want there, and there will be like 5 or 6 questions. Okay, so I think that's for today. If I have time, I will try to discuss the assignments, but maybe it's not in the short term. But yeah, I will update if there is. I will let you know if there is any update on that. Please make sure that, oh yeah, please make sure that you work on the exercise in the myITS classroom to get the attendance of this class. And yeah, I will see you probably, yeah, on October 31st. Yeah, if I have time, I will try to discuss some assignments, but I'm not so sure about that. Okay, yeah, so thank you. Yeah, we'll see you next time. Thanks.